This is our second mini lecture on this module on enzymes. Today we're going to focus on how to name enzymes, also known as enzyme nomenclature. There are two strategies for naming enzymes. Let's go over the first strategy. The first strategy is to add the suffix ase to the substrate of the reaction. So as you can see in this reaction, the substrate is lactose. So we take off the OSE and add an ASE. So now the enzyme for this reaction would be lactase. Okay, and it is. So this would be lactase is the enzyme for the breakdown of lactose. So here the substrate is lactose, so the enzyme is lactase. The second strategy involves adding the suffix ase to the reaction being catalyzed. So in this example, we have a reaction of a dehydrogenase reaction where we're removing hydrogens from the main substrate. And so we have the dehydrogenation of an alcohol. So in this case, the enzyme would be alcohol dehydrogenase. So you're naming it based on the reaction, not based on the substrate or the reactant. These are the two naming strategies for enzymes. Based on what we just went over, let's check your learning. What are the two possible names for the enzyme that catalyzes the following reaction? So we have maltose interacting with a water to form glucose and glucose. So in this case, we could, based on the first naming strategy, add an ase to the substrate. So the enzyme could be maltase. If we named this reaction, or the enzyme, based on the second strategy, which is naming it based on the reaction, we have to first identify what is happening to maltose. Well, it's undergoing a hydrolysis reaction. It is gaining water and splitting into two products. So in this case, the enzyme could also be maltose hydrolase, where we add an ASE to the reaction catalyzed, which is a hydrolysis of maltose. So in this case, it could be maltose hydrolase. If the enzyme was not specific to maltose, but to any disaccharide in general, it would be called disaccharide hydrolase. Okay, so the two naming, we have maltase as the enzyme based on the first naming strategy, or based on the second strategy, which is naming the reaction, we would have maltose hydrolase. If it was based on the second question on the screen here of to disaccharides in general, it would be a disaccharide hydrolase. Now let's move into the second topic for this mini lecture, which is about enzyme kinetics. Kinetics is the study of reaction rates in a chemical reaction. So that's what we're going to look at for the following slides. Factors that affect kinetics include the nature of the reactants, the phase of the reactants, whether they're in a solid state, liquid, or a gaseous state, the concentration of the reactants or the concentration of the substrates, the temperature within the body to catalyze that reaction, the amount of free energy available, and then, of course, catalysts, which are the enzymes. So all of these factors affect kinetics, the study of the rate of reactions within a chemical reaction. Now let's get a little bit more specific. Now we're going to define what enzyme kinetics is. So enzyme kinetics is the study of reaction rates in enzyme catalyzed reactions. So enzyme kinetics is studied by when we incubate an enzyme with its substrates at a defined temperature and pH, and following the formation of product over time. The rate of formation of a product slows over time, and we'll look at that today, which is due to accumulation of the product and therefore loss of the substrate. So when we have a lot of product made that the body needs, we then get feedback to say, okay, let's stop this reaction. And so the product formation slows over time once the supply has met the demand. Many students in the past have stumbled when it comes down to understanding enzyme kinetics. So I want you to not be distracted right now and really focus on this slide because this is an important figure that I really need you to understand. On the y-axis, we have product formed. On the x-axis, it's time. So as you can see, the green line talks about the initial rate of a reaction. And as you can see, it is very, very fast. We have a lot of product formed in a short period of time. And this is because we have lots of substrate available within the cell, lots of substrate to interact, and therefore the product formed happens really, really quickly. But as you can see with the line that's black, that the product formation dampens over time. And this is because we've lost substrate. We don't have this infinite amount of substrate available. So over time, the substrate will decrease, and this will decrease the amount of product that can be formed. Okay, so the high rate of the reaction at first is due to a lot of substrate. And then what we see is the curve dampens. And this is due to a reduced rate later as a result of a loss of a substrate. So really what it comes down is to substrate concentration. How much substrate do you have or reactants are available within the cell for the reaction to happen? Okay, when you have a high amount of substrates available, which is at the beginning of the reaction, the product formed will happen very, very quickly. The reaction will happen very fast. But as you use up all that substrate, as the concentration of the substrate within the cell decreases, then the reaction decreases and the product formed will decrease. And that's a result of substrate concentration. We also have something called feedback inhibition. This is very important because key metabolic enzymes are often inhibited by the end product of the pathway they control. This is called feedback inhibition. When there's enough product form, then the enzyme can sometimes be inhibited, and therefore no more product is being formed. And this really comes down to that supply-demand relationship. Once the demand is met by the supply, then that reaction doesn't have to happen as much. And therefore, the enzyme can sometimes be inhibited by how much product is formed. My analogy for this comes back to Amazon. Amazon, at some points of time throughout the season, can have a huge demand for certain toys, especially around Christmas. But once that supply of the factory has met the demand for toys, then the production of that toy will decrease. That it's all about a supply-demand relationship. This happens in the body as well, specifically around enzymes. That once there's a huge demand for the product to be formed, once we get that product, then we don't have to shuttle through this reaction as quickly. That once the supply and the demand are in line, then the amount of product formed will decrease. Another concept that's extremely important is enzyme saturation. There's only so many enzymes within the cell. You may have a lot of substrates, but you might not have enough enzymes for that substrate to interact with. And this is called enzyme saturation, where all the enzymes are already saturated with substrate. So let's look at this for a second. At low substrate concentrations, there is a low rate of reaction. That's what we showed on the previous slide. When there's not much substrate available, then the reaction will not necessarily happen that fast. Okay, it's all based on substrate concentration. As substrate concentration increases, that means there's more substrate available, the reaction rate also increases. However, if we see an even greater increase in substrate concentration, the reaction rate will slow down due to saturation of the enzyme. That there's only a certain amount of substrate concentration for that enzyme, that we're limited by the enzyme saturation. Let's examine the effect of substrate concentration and enzyme saturation a bit more. Specifically, I want to draw your attention to the figure on the right. We see that this curve is increasing and then flattens. So A and B is really a function of we have enough enzyme, which are like the Pac-Mans. We see them in yellow. And then the substrates are in red. So the more substrate you have, the faster the reaction goes. Then we get to C and D, whereby we have a lot of substrate, but we don't have enough enzymes. As you can see, every enzyme, every yellow little Pac-Man, is filled with substrate. And so we have enzyme saturation. So in this case, we could have a lot of substrate, but if we don't have enough enzymes for it, then we're limited in the rate of the reaction. So there's really two limiting factors to the rate of reactions of enzyme reactions. Number one is substrate concentration. If you have a lot of substrate available, then you can have a high rate of reaction. But then you get to a point where you don't have enough enzymes. So enzyme saturation is the second factor that affects the rate of reactions. So you may have lots of substrate, which means a fast rate of reaction. However, there's only so many enzymes. Once the enzymes are saturated or filled with substrate, then the rate of the reaction will decrease. That there ultimately is a ceiling effect when it comes to substrate concentration, which provides a limitation by the number of enzymes. So one thing with exercise training is we can increase the number of enzymes, and therefore the rate of the reaction isn't limited necessarily. That enzyme saturation is less of a limitation to substrate concentration with exercise training. In order for biochemists to understand enzyme kinetics, we isolate a substrate with its enzyme in a petri dish at a set pH and a set temperature, and we measure the activity. Now, there are various constants that are used to describe the rate of reaction, and I want to define them right now, and I'll explain them on the next slide to make it a little bit more clear. Km is known as something called the Michaelis constant, which is used to understand enzyme kinetics. Then there are a few different things that I want to define. Vmax is the maximum rate of a chemical reaction. So V could be velocity. So the velocity maximum, how fast that reaction is happening. A half of Vmax is the half of the maximal reaction rate. Okay, Km is a measure of the affinity of an enzyme for its substrate. So affinity is attractiveness. How attractive is that enzyme for its substrate? So the substrate concentration at which an enzyme works at half its maximum rate, or half Vmax. Km is also the point where half of the active sites on the enzyme are occupied for the substrate, so we see half enzyme saturation. And then the higher affinity or attractiveness of the enzyme for the substrate is equal to a lower concentration that is needed for the Km. I know this is a bit confusing potentially right now. Let's explore it further on the next slide. So this figure showcases the Michaelis-Menten saturation curve. That essentially we have our pieces that we defined on the previous slide. We have Km on the x-axis, which is the concentration of the substrate at half the maximum reaction rate, or 0.5 Vmax. So half of Vmax, or 0.5 Vmax, is defined as half of the maximal reaction rate. Vmax on the y-axis is the maximum reaction rate. So we can see that Km, if we draw the dotted outline up from Km, remember Km is the concentration of substrate that elicits a half of the maximum reaction rate. So we get there quite fast. We don't need very much substrate to get to a high rate of the reaction. What happens though is this curve flattens over time, and that's a result of the enzyme getting fully saturated with the substrate. Despite the concentration of the substrate on the x-axis increasing over time, the reaction speed is limited by the amount of enzyme you have. That if the enzyme is fully saturated, that's why we see a plateau in the curve. Ultimately, this figure is important in showing the relationship between the concentration of the substrate, the velocity of a reaction, and the impact of enzyme saturation on the maximum reaction rate. This figure showcases two different enzyme reactions, enzyme A, which is in the red line, and enzyme B, which is the blue line. So the y-axis, we have the rate or velocity of a reaction. The x-axis, we have the substrate concentration. So as you move to the right, we have more substrate concentration, more available substrate within the cell for a reaction to happen. So this figure demonstrates the relationship between substrate concentration or substrate availability and how fast a reaction happens. So let's first consider enzyme A, which is in red. This has a low Km. That means it doesn't need much substrate to get to half the reaction's maximum velocity. That means the reaction happens very quickly, that you don't need too much substrate within the cell to get to maximum velocity. So as we can see, as soon as you see that plateau in the curve, that's the maximum velocity is achieved. We have enzyme saturation. It happens quite quickly, as you can see in this curve, and that we get to that plateaued curve. This means the enzyme has a high affinity for the substrate and the reaction happens very quickly. Now let's consider enzyme B, which has a high Km. That means the enzyme needs a higher substrate concentration for the reaction to reach half of its maximum velocity. Thus, it takes longer for the reaction to get to maximum velocity. So this means that the enzyme has a lower affinity for its substrate. That enzyme needs a high substrate concentration for it to do its job and to do the reaction fast. So ultimately, enzyme A is more favorable. This is the way that you want an enzyme to be, that you don't need too much substrate in order for the reaction to go to its maximum speed right away. What we see with exercise training is that we can increase the substrate concentration within the cell. We can increase the number of enzymes so they don't get saturated as quickly. And we increase the enzyme's sensitivity or their affinity for the substrate, which all combined increases the rate of reactions. So you're probably wondering, why do we even care about Michaelis constant or Km in biochemistry? Well, just as a recall, all reactions in biochemistry are catalyzed by enzymes. If we didn't have enzymes, we wouldn't be able to function and we would die because the reactions within our body wouldn't happen fast enough. As well, each enzyme has its own Km value. That's the amount of substrate that's needed to get to half the maximum velocity of a reaction. So this is important because it tells us how reactions are going to occur within the body. Do we need a high concentration of substrates? Do we need a low amount? What tissues will we find these concentrations in and under what conditions? So for example, in your vital organs, we have a high substrate concentration, which makes sense because we always want reactions to happen. So remember, vital organs, we have a high substrate concentration to promote a constant supply of biochemical reactants to fuel these reactions, specific to energy production. Most enzymes in vital organs have a low Km. That means that the enzymes have a high attraction to the substrate, that we don't need much substrate to cause reactions to happen fast. This all makes sense because you want your vital organs to be able to go through these reactions very, very quickly to meet the demands of the body for us to be able to survive and function. Here is a nice summary figure of enzyme kinetics. We see on the x-axis the concentration of the substrate, and we see on the y-axis the velocity of the reaction. And this is a typical pattern of an enzyme. We see a fast velocity at first, and then it plateaus as a result of the enzyme being saturated with substrate at the maximum velocity. And that means that the reaction has gone to completion, that we have product formation happening. So we defined key variables here. We have our Km, which is that concentration of the substrate to get to half the maximum velocity of a reaction. And then we have our Vmax, which is the maximum velocity of that reaction, where we essentially have enzyme saturation. Another important piece that I want to showcase on this figure is the dotted line on the bottom that's highlighted in yellow. This is what would happen if we had a non-catalyzed reaction. So this is the biochemical reaction would not occur at a detectable rate if uncatalyzed. And so that just shows how slow the reaction would be without an enzyme. Now let's go over briefly the Michaelis-Menten equation, which helps us quantify the rate of reactions. That ultimately, this equation describes how reaction velocity changes with substrate concentration. It assumes that there is a much greater concentration of substrate than there is enzyme, and it also assumes that the rate of formation of the enzyme-substrate complex is equal to the rate of dissociation of the product and the enzyme. So here we have VO is equal, VO is the reaction velocity, is equal to Vmax, the maximum reaction velocity, times the substrate concentration, divided by the Km, which is the Michaelis constant, which is the amount of substrate that's needed to get to half of Vmax, plus the substrate concentration. So again, it assumes greater concentration of substrate than enzyme, and that the rate of formation of the enzyme substrate complex is equal to the rate of dissociation. So what does this mean? Well, let's go over an example on the next slide. Now let's try this out. Let's do an equation together. You can pause the recording right now and try this on your own if you wish. So the question is, what would the reaction velocity be of a reaction catalyzed by a classical Michaelis-Menten enzyme given the following? So we have VO, which is unknown. That's what we're trying to solve for. We have velocity maximum, which is equal to 2.5 millimoles per minute. We have our Michaelis constant, or Km, which is 2.5, and our substrate concentration, which is 5 millimoles. So based on the equation from the previous slide, we would have the 2.5 times the 5, which is the substrate concentration, divided by the 2.5 Michaelis constant, plus 5 millimoles, which is the substrate concentration, which you should get 1.6 millimoles per minute. Okay, so this is how fast the reaction would be given this situation, given these parameters, these variables. So what would happen if we decrease the substrate concentration to half the amount, from 5 millimoles to 2.5 millimoles per minute? How would the rate of the reaction change? Well, if that was the case, if we drop the substrate concentration, or S with the brackets around it, from 5 millimoles to 2.5, we would see that the rate of the reaction would drop to 1.25 millimoles per minute, showcasing that this whole reaction, that a rate of the reaction of an enzyme is significantly affected by the concentration of the substrate. This concludes the learning for this mini lecture.